Great. Thank you very much, Marcel. Where can I put this? All right, so yes, I work at DeepMind. I've been leading a research group there for about the last 4 years, in which time we've grown from about 50 people to over 500 people, making us sort of I think we're the largest research institute focusing on machine learning in the world, which is a lot of fun. So I'm going to talk about some of my research here, and I've got a lot of slides because I can never decide what not to talk about. I want to talk about everything. But the main question is, can we do end-to-end deep learning for learning robotics tasks? And can we achieve new state-of-the-art if we can do this? And first, a bit of history. So in 2010, or prior to 2010, the state-of-the-art for doing speech recognition looked something like this. It was a set of models that were each machine learning models that were trained using a fair amount of domain knowledge to go directly from the input, which was an audio signal, to the output, which would be text. And in 2010, this changed because the new state-of-the-art became a deep network that was trained end-to-end using a single model, meaning that gradients were used to optimize the model through the whole thing to go all the way from the desired output of text back to the input that was audio. In 2012, I remember this well because I was in the computer vision field, and I was working on convolutional networks at the time, and so it was a lot of fun, honestly, to see that the state-of-the-art in computer vision got exceeded substantially on the ImageNet challenge by using a deep neural network, AlexNet, which really sort of changed deep learning. And similar thing has happened in machine translation. We've gone from a set of a set of models, a modular approach, which involved various pieces, to being an end-to-end trained deep neural network, again, exceeding the state-of-the-art in that field and becoming the new state-of-the-art approach. And if we look at robotics in 2018, I have 2017 on there, but it applies now, then this looks sort of the same. We have an input, we have raw sensors. We typically feed those through some sort of a perception stack where we might identify objects, for instance. That information would populate a world model. We'd then run some planning algorithms, feed this to a controller, and produce an action of the robot. And I really think that we simply need to find the right algorithm such that we can train a deep neural network end-to-end, all the way from sensors to actions to do complex tasks on real robots. But we're not there yet. So why? Well, different from all of those other tasks, robots can't be trained very well using simply a nice data set with a set of labels. That's because with robotics, we have sensors and we have actions, and we're really learning from a sequence of interactions where the environment changes as an agent, as the robot takes actions in the world. And that makes it much more complicated to learn. What we do have is deep reinforcement learning, and this has really been DeepMind's contribution in the last few years, is to bring together the framework of reinforcement learning with deep neural networks. So this could pave the way. This is a way to learn from interaction in environments, to optimize a policy from sensory observations of the world and to produce actions in an environment. And this has worked very well for some things. So if you look at how we play Atari games, for instance, then DeepMind has trained neural networks in order to play better than any human on some 3/4 of the Atari games that are used. For instance, this agent, I don't know if you noticed, but it's not only a good player, but it's also very bullet efficient. So not a single bullet is wasted here. Everyone meets its target as it clears level after level. And boom. Oh, fun to watch. This also works with robots nicely. We can take, a couple years ago, I said, well, what happens if we take exactly the same approach, the same neural network, the same learner, and we instead apply it to the problem of grasping, of just reaching to a 3D location. So basically learning the forward dynamics, kinematics of a robot. So we're just feeding in the RGB observations and we're producing a discretized action for each of the 9 degrees of freedom, the 9 joints of this robot. And we can very quickly learn how to reach in space. So this seems to show that we can learn the model of a robot and how to operate it within, again, this end-to-end sensory motor sort of approach. But problems. If we really want to work with real robots, we need to solve some fundamental problems. So, can deep reinforcement learning agents learn multiple tasks and learn to compose tasks over time? Can DeepRL agents learn efficiently without needing 100 million steps of experience? Can DeepRL agents learn from real data rather than perfect simulations? And can DeepRL agents learn continuous control? So let me head through some of these different areas quickly. So the first one I'll talk about is multiple tasks and lifelong learning. And this is something, if I had to solve only one of those problems, I would solve this one, because I actually think that this is the one that's most fundamental. If we can learn multiple skills over time without forgetting, and if we can learn to compose different skills to learn more complexity and to get the sort of combinatorial explosion of capabilities that would result in, then we would be able to solve deep learning for robotics. So the 3 challenges for lifelong learning I take as being 1, catastrophic forgetting, 2, getting positive transfer as you learn from task to task, and the third one is being able to handle both specialization and generalization. So catastrophic forgetting, first, is a well-known problem. It's especially bad in DeepRL, where we get agents that if you train them to a perfect performance and then you perturb their weights just a little bit, then they fall off the cliff of performance, can no longer solve a task. We can see this here. This is an agent trained to play Pong. So the agent is controlling the green paddle there on the right, and it will just very quickly win the game perfectly, 20-0. If we take that same agent and we simply perturb the screen a little bit, it's probably hard to even see what I've done here. All I've done is color the opponent's paddle and score black instead of orange. And it means that while the agent controlling the green paddle is still moving around, it's actually missing every time. And it will lose 0-20. If we simply invert the colors and go to this other screen, which I don't have to tell you, this would not be a problem for any self-respecting 10-year-old, then the agent completely gives up, doesn't even move around, and loses even more quickly. So this is evidence of how fragile these trained networks can be. One of the approaches we use to deal with this, there's a lot of interesting work in this field. The one that we worked on is something called elastic weight consolidation here. The idea is that when I move from learning on a first game, task A, then I've learned a set of parameters, theta star, and when I learn a second task, if I learn it directly using SGD, then I'm going to immediately forget and lose performance on task A. If I apply some regularization, say L2, then that's going to simply slow down my learning, but not make me not forget how to perform on task A. Instead, what I would like to do is move in my parameter space in such a way that I can now perform on task B while not forgetting how to perform on task A. And we do this by adding a regularization term. We use an estimate of the Fisher information in order to elastically scale the weight update. This way, we have an estimate of which parameters are the most sensitive to the performance on task A, and I want to keep those parameters closer, so more stiffness, my movement in those parameters, while being able to move in other parameters which are not as critical for the performance on task A. And And this allowed us to train one single neural network on, say, 10 different Atari games, something which hadn't been done before. Other approaches: what if my tasks really don't get along? In looking at this problem of catastrophic forgetting, we said, well, what if we really want to be able to cement the knowledge of the performance on that first task while I go on and play a second task? But I still want to have transfer. I still want to be able to use the knowledge that I learned on task A to be able to do better on task B. So we came up with an architecture that we called progressive neural nets. Here we train a single column, a single neural network, to perform on one game. And then when we move to a second game, we're going to freeze that first column, but we're going to have these lateral neural connections from every layer of the previously learned networks to the new column. And this is going to allow us to opportunistically reuse the features that were learned, either low-level vision features, mid-level vision features, maybe higher-level policy features. And that'll allow us to reuse those if they're valuable when we learn a second task, without disturbing the performance on the first one. We can keep on doing this. We can keep on adding column after column, and we show that we need less and less of that new capacity for each new task that we learn, and that we get a lot of forward transfer that's more stable than other sorts of methods like fine-tuning. So this has been used for not only for learning sequences of Atari tasks, which is a very important problem, but also for, I think, the more interesting problem of doing sim-to-real learning. So this is training an agent first in simulation, where we can have lots of data and lots of time to run lots of asynchronous agents at the same time, and we can learn a task. And then we can add a progressive network and train just that new network on a real robot that's analogous to the one in simulation. That allows us to cross that reality gap in a more stable way than you get through, for instance, fine-tuning. And then once we've sort of crossed that reality gap, and now we have an agent that can solve some task on the real robot, now we can keep on changing that. So I add task B, task C, task E, and continue to grow and expand on a set of skills on the real robot. And one more sort of example of an architecture that can work for lifelong learning. And this is called Distral. Which stands for Distill and Transfer Learning. And this is sort of an ensemble architecture with a bit of a twist. So here we want to train several different architectures, several different neural networks at the same time. So represented here, we're learning Pi1, Pi2, Pi3, Pi4. 4 different neural networks on 4 different domains, but we're also learning a Pi0 at the same time. And the way in which we're learning these is to simply apply a constraint on the KL divergence between that central task and the prior task, and all of the domain-specific ones. And this allows us to do not only the effect of this is that we get distillation of knowledge from the games to that center Pi0 agent, but we also get regularization, so we get more stable learning by that ensemble of task-specific learners. So this could be one way of getting past the need for generalization as well as specialization when we solve these sort of deep RL tasks that are not as amenable, I must point out, to doing these sort of one big network and train lots of different tasks off of that. That really doesn't work well in deep RL. All right, and this has allowed us to play lots of Atari games at the same time, like I said, make some progress on sim-to-real for robotics, and we've also done other sorts of mazes and things like this in terms of the results. The next thing I'd like to take a look at is how we can speed up learning. And to look at this, we were doing navigation tasks, and we were trying to solve these problems where the agent would get spawned in a maze, and it would need to explore the maze to find some goal location. As soon as it found that goal location, it would get respawned somewhere else, and it would need to find its way back again. So it was an explore, remember, and then exploit. And then that would be one episode, and then you'd start a new episode with a new maze. And this is a really hard problem. So it was taking the agents a very, very long time to learn them at all. to learn how to sort of solve this problem, how to use things like memory in order to be able to remember where the goal location is. So to quickly run through, we came up with an architecture. We sort of kept on adding things onto it. It's too much fun. So we start out with a convnet. We add an LSTM, which is important for memory. This is obviously a problem that requires memory because we need to recognize the goal, remember where we've seen it so that we can make our way back to it, the agent can. So we actually used a stacked LSTM here with a skip connection. We added in a couple of additional inputs, so being able to see what the previous reward was and also what the previous action was and what the velocity of the agent is over time. And this is trained using A3C, which is Asynchronous Advantage Actor Critic. And here's the critical thing that I want to point out, is that we added an auxiliary loss. So we added a loss that was sort of self-supervised. So the agent had the input is an image, which is RGB and D, so there is a depth layer. And instead of providing the depth layer as being an input to the system, we use the depth layer as being something to be predicted by the system. So it never sees what the depth is of the current image. It just tries to predict what it is. And we could either have it predict depth using, so this is just using a softmax classifier off of the convolutional features, or we could have it be on top of the LSTMs, so predicting it from the hidden state of the LSTMs over time. And we also tried using an auxiliary loss, which was a predicting loop closure. So this was just a Bernoulli loss saying, have we closed the loop on this particular path of this particular episode in this particular maze or not? So obviously this would help the agent to have a better memory for where it's been before. So these are sort of some of the different architectures that we looked at. And we tested this. So let me show you the results that we found when we looked at, this is a large maze. It takes a human, actually, a long time to solve this. Episode lasts for about 5 minutes. And you're trying to find this goal, find your way back to it, no matter where you start. If we look at just the feed-forward agent, so without a LSTM, it takes a long time to learn anything. The scale at the bottom is at 100 million frames of experience. If we add the LSTMs to the memory, it sort of gets the problem, but takes a while to get there. The learning curve stays flat for a long time. If we add sort of the second LSTM and the additional inputs, then we do a little bit better. And if we add the loop closure prediction, auxiliary loss, then we see that that learning, that takeoff and learning moves a lot to the left, which is what we want to see. But it looks even better when we predict depth. And this is because, and it gets even a little bit better if we look at the depth as predicted from the LSTM and looking at depth and loop closure predictions together. And now we see that we're learning extremely quickly how to do well, and we do much better than a human does in the end. So this is exciting, mainly because of the improvement in data efficiency to learn a very complex problem that we really couldn't learn at all without adding some of these architectural improvements. And the real key here is that we're not learning just using sparse rewards. We're learning using dense gradients that help the agent to make sense of the observation that it's getting and learn a representation of the world that makes sense by using that depth prediction. And this is what this looks like, zooming around a maze. So we get a +1 for running into apples. And then we have to zoom around until eventually we will find the goal location, which is here. And immediately the agent gets respawned somewhere else and needs to traverse the maze again. It doesn't always take the most optimal path on the very second trajectory. As you can see here, it's sort of taking the long way around again. But what we do see is that over the course of an episode, the amount of time it takes to the goal gets shorter and shorter and shorter. So it is using its memory throughout that episode to learn the structure of the maze and to remember where the goal location is. All right, next I'm going to talk about StreetLearn, and this is a project that I've been working on because I got frustrated with sort of the synthetic quality of the mazes that we were using to think about navigation problems, and I really wanted something that used more real data. And so I felt like the best place to go would be the real world and a real map of the real world. And so what we ended up using was Street View. So we took Google Street View and we turned that into an interactive reinforcement learning environment. So here, the underlying structure, which is never observed by the agent, instead of looking like this, now looks something like this. The agent never sees that, but that is the underlying graph, and the images are now much more rich and noisy and complicated. And the agent still has to decide on it has the same sort of actions and moves through the space. It only ever sees the RGB information in this case. And so we have an environment, for instance, that covers most of Manhattan and New York City. And we're able to get a lot of diversity of different types of areas of this. There's tunnels, actual tunnels, which are complicated for the agent to figure out. And we designed a game that we call the Courier task. And the idea here is that you're going to spawn somewhere in Manhattan, and you need to navigate to a target location that's given to you, sort of like a taxi task. You're given a location, and the location is given to you by its distance to a few fixed landmarks. So it might be south of the Empire State Building and west of some other location. And the agent is going to try to find this location, and it's going to start receiving reward as it gets within 100 meters or 200 meters, I think, of the goal location. And then once it actually gets to the goal, then it's going to get given a new destination to get to, a new courier destination. And we have an architecture which, again, relies on A3C underneath the hood and involves both a global pathway and a relative pathway. And so here we start with the sort of central component is the image is fed into a convolutional neural network and to an LSTM, and it produces a policy, how the agent should move. The target location, that representation of where it should go to based on landmarks in the city is not given to this part of the architecture, it's given to a separate LSTM. This means we'd be able to replace this so you could learn a different sort of global embedding of your world if you're in London or you're in Paris, or if you're in New York. And then we also have another LSTM that helps the agent have a smooth and consistent local policy for how it moves. So this is a little bit of a noisy video, sorry. And this is the video is a little bit low resolution, but that's the resolution that the agent is seeing, and I believe in sort of truth in advertising. So it's a bit blurry, but this is what the agent sees. And if you look at the video first, at the images, then you'll see that the agent spins around here and there, and then decides, okay, I'm heading this way. Figures out where it is by looking around, and then figures out which direction it needs to go. On the right, you can see the red dot. That's the target location, and once it gets within a couple blocks of it, then it's going to get another location that it needs to get to. So it's gotten its full reward at that point, and now it needs to get to the next one, and now it moves along. And so this is one part memorization of the graph, and one part being able to really learn a policy for navigation, where you need to learn what the world looks like, what do turns look like, how do I understand this information. And we've shown that you can still navigate even if you block out portions of the graph so that you need to navigate around them. And then after training, under test conditions, you're asked to navigate through those unknown areas. And you're still able to do that. So I'm very excited by this line of work. I think it's a really fun way to get real world data and use it for doing deep reinforcement learning. All right, in my last minute, let me just mention continuous control. So this is work that's been done. The interesting part of this for me is about how you manage different types of observations. So if you have the case of a humanoid figure, then you have these different types of observations. Some are about the body, proprioceptive information near the body, and some of them are exteroceptive observations, things about your environment. And so what my colleague Nicholas Hees has found is that it's really valuable to separate out these two different types of observations and treat them a little bit differently. That way you can transfer, for instance, knowledge of the body to doing different tasks in different environments. So the training here relies on an architecture that separates the type of observations, and it's trained using TRPO. And over these different environments. And what we get is these really nice learned behaviors. They're not as accurate as using a nice musculoskeletal model like Lucas presented yesterday, but they do show that we're able to learn different types of bodies, how they succeed, and really, the agent doesn't have any reason not to throw its arm around. It's actually just reducing variance by throwing it to the end of it, to its joint limits. And it really makes sense from an optimization point of view. And the impressive thing here is not just that we're able to learn these tasks, is that this is one neural network that's learned all of these different tasks. So it's learned a really strong grounding of how to move that body to solve all of these different obstacle courses with one neural network, with one policy. And that's sort of the impressive thing here, is the robustness and the flexibility of this neural network for different environments. All right, so again, these are some of the questions that I think we need to answer and bring together if we're really going to bring end-to-end deep learning for robotics, have it work well. And these are some of the different papers that I talked about, if you want to look at more details of them. And thank you very much.